In this video, we're going to talk about the theorem of calculus, and we're going to focus on part 1. This is a theorem that ties together all of integration theory with all of derivative theory, so it's pretty fundamental to calculus. I'm going to start off by considering an example. Just like we saw in the first lab, let's suppose that we have a bicycle that's riding along with constant velocity. Let's say that we have a velocity of 10 miles per hour. So I'll label this v of t over time. So this is my velocity curve. And over here, I'm going to have my distance curve. So s of t, representing the distance that's being traveled, distance of the same bicycle. And I'm going to suppose that I start at time 0 at a distance of 0. And given this rate, we see that every hour the number of miles that's traveled is going to increase by 10. So after 1 hour, I'll be at 10 miles. After 2 hours, I'll be at 20 miles, and so on. And the question that I want to ask is, how far does the bike travel from t equals 1 to t equals 3 in hours? And let's label this. And I'm going to answer that question two different ways using these two different graphs. And this is a really simplistic situation, but it develops the intuition behind the fundamental theorem of calculus. So just looking at the velocity curve, if I wanted to know how far the bike traveled, I can use the fact that distance is just going to be the product of speed times time. And speed is just the magnitude of velocity, in this case 10 miles per hour. And I know that I'm traveling from t equals 1 to t equals 3. So without doing any calculus, I could say that, oh, the distance traveled is going to be 10 miles per hour times a total of 2 hours, which ends up being 20. But if I were to consider this using calculus, I could also consider the total distance traveled to be the area under my velocity curve. And notice that the components of the area correspond exactly with the multiplication that we did previously. That I see, even if this weren't a straight curve, we could have some sort of variable velocity. And we would see that the height in each case is representing the speed. And so that means that the height is going to be this function v of t. And I'm going to examine the area under that curve as t ranges from 1 to 3, represented as the definite integral from 1 to 3 dt. Filling in this, I know that my velocity is actually just the constant function 10. Maybe I could write this as the integral of 1 to 3 of 10 dt. And without doing a lot of formal notation, we see that this integral is indeed going to be the value of 20. Now let's consider this from a second perspective. Instead of using the velocity curve, let's use this distance function s of t. And we decided that s of t, because we're traveling at a constant rate of 10 miles per hour, is actually just 10t. It's a linear curve with a slope of 10. Using this function, if I want to know how far the bike travels from t equals 1 to t equals, to see how far did it travel previously, and then how far did it travel by the time it got to 3 hours. And I would want to know what the difference in distances traveled. Notationally, that's going to be the difference between the total distance that it's traveled. Maybe I'll say s is the name of this function, so s of 3, the distance after 3 hours, and I'm going to subtract off how much it traveled in the first hour, minus s of 1. And reading off in this graph, that's going to be s of 3 is 30, and s of 1 is 10, which gives me a total of 20 miles. Now, why did we all do all of this in this simplistic example? The simplistic example sets up the fundamental theorem of calculus. What we found was that the area under this velocity curve can be computed using the net change in this distance curve. So here's the formal statement of the fundamental theorem of calculus part 1. The formal statement says that the definite integral of the function little f of x dx is equal to the difference of big F of b minus big F of a, where the relationship between little f and big F is that the derivative of big F is little f. So what is all of this saying? This is saying that the integral of a function f of x from a to b can be computed by finding the net change in the antiderivative function. So in our example that we saw, our little f function was a really boring function, our little 10. So when I want to compute the integral from 1 to 3 of 10, in this case dt, I can do so by finding the antiderivative of 10. So I think to myself, the antiderivative is the function that when I take the derivative of it, it gives me back the value of 10. So one antiderivative would be the function big F of t. Maybe I'm switching variables. Let's stick with t's. Big F of t would be 10t. I know that this is an antiderivative, as when I take its derivative, I end up with 10. And this is telling me, by the fundamental theorem of calculus, if I want to compute this definite integral, I can plug in the net change. And notice that I want to plug in, this is going to be 10t evaluated at the value of 3, because this is my upper bound, and then I want to subtract out what I had with my initial value. So this ends up being 30 minus 20, 10 times 1 is 10, which equals 20. This is exactly what we saw before, but here's some formal mathematics to work it out. Wait a minute though. One of the things that we talked about previously, the distinction between an antiderivative and the antiderivative, what about the plus c? So in this example, I just picked 10t as my antiderivative function, but what if I had had a plus c in this? What if I had picked a different antiderivative function? So the short answer is the plus c part will cancel out. And you can see that algebraically with this same example. Suppose I choose the generic antiderivative. So again, let our original function f of t be equal to 10. And then I could say my derivative, the general antiderivative, is going to be equal to 10t plus c, because we could add any constant, and when I take its derivative, I end up back at this function. And notice that when I apply the fundamental theorem of calculus using this generic antiderivative, I'm taking the integral from 1 to 3 of my f of t function. If I plug in the upper bound into this function, I'll do a little scratch work. F of 3 in this case is going to be 10 times 3 plus c. And f of 1 is going to be 10 times 1 plus c. That means that the difference, f of 3 minus f of 1, is going to be equal to this plus c minus this whole thing, 10 plus c. And you see that the plus c's cancel. I end up with 30 plus c minus 10 minus c, which is indeed equal to 20. I could also see this graphically. Maybe this is going longer than you would like, but I think that it's helpful to see 10 miles per hour. Here's my boring f of t function, my velocity function in this example. And let's say that I had picked a different antiderivative to be the distance function. Let's say that for this particular bike trip, it's the second day into the trip, so I started at some plus c value of 15, for example. So let's say that I choose a new antiderivative function to be the function big F of t is equal to 10t plus 15. This is similar to the antiderivative function that we had previously of just 10t, but I started with an initial condition of a plus 15. Notice that means that after 1 hour, instead of being at 10, I'm 5. For 3 hours, instead of being at 30, I'm going to be at 45. But the net change is the same, and that's exactly what the fundamental theorem of calculus is telling us. We see that the net change, and maybe I'll write in this example, the integral from 1 to 3 of 10 dt is still going to be the change f of 3 minus f of 1. It's just in this case, change is going to be 45 minus 25, which is still 20 miles. Whereas previously, here's our old f of t function. The net change in the outputs is still going to be the same. So let's do an example. So suppose I want to compute the definite integral from 0 to pi of a little f function sine of theta d theta. And in order to do this, to compute any limits, I can use the fundamental calculus, and I know that this is the net change in the antiderivative of the sine of theta. So I need to think to myself, here's my thought bubble, what is the an antiderivative of sine of theta? I know that the derivative of sine is cosine, but we don't want the derivative of sine, we want the antiderivative. And so that means that antiderivative of sine is negative cosine. That's what I think to myself, because the only one I have memorized is the derivative of sine is cosine. So the antiderivative must have been negative cosine. So now I know what the antiderivative function is. I can say, aha, my capital F function, my antiderivative function, is equal to negative cosine of theta. So I'm going to compute this by finding f of pi, f of the upper bound, minus f of 0, f of the lower bound, where f in this case is my negative cosine theta function. So in this case, this is the negative cosine of pi minus, and we have to be careful of signs, negative cosine of 0. And what do we have here? The cosine of pi is negative 1. So the negative of negative 1 is actually a positive 1. The cosine of 0 is 1. The negative of 1, and this is the negative of the negative of 1, which is positive 1. Right? Following all the signs on that. So it means that this integral should be 1 plus 1, which is equal to 2. And we can check this graphically to see if this makes sense. So remember, our sine curve looks something like this, and it continues on periodically, but we're only interested in the integral from 0 to pi, which is in the first upper portion of this loop. And we're saying that the area under the sine curve from 0 to pi is about equal to 2. And just looking at this, I know that this sine curve has a maximum height of 1. That sort of makes sense. About 3 in the base, about 1 in the height, about an area of 2 makes sense. So this is my function. This is my little f function, f of theta. And let's change theorem. So over here, our capital F function, our antiderivative function, we found was going to be negative cosine of theta. So negative cosine theta, recall the cosine function is the one that's also periodic, but it's going to start down here at -1 because and at pi, it's going to be up here at 1, and then it continues looping onwards as well. So by our net change, we're saying that our antiderivative function, the net change in our antiderivative, is and outputs from pi, which, because this function is negative cosine theta, this value is 1. And here we have f of 0, which is down here at -1, and our net change is exactly 2, which is what we found when we computed our antiderivative. Let's do another example. Suppose that I want to find the integral from 1 to 2 of dx divided by x. Just to get started on this is a common way to write the notation, but I think that it can sometimes seem confusing, that this is actually just 1 over x dx. This is the function 1 over x, is my little f function. So again, I think to myself, oh, I just need to apply the fundamental theorem of calculus. This is the same thing as my upper bound minus my lower bound of some function f, and I need to figure out, well, what is that antiderivative function? And we talked about in a previous video that an antiderivative of the function f of x equals 1 over x is the function absolute value of the natural log of x. So I know that's the function. So because the absolute value of the natural log of x, the natural log of the absolute value of x is an antiderivative, I know that by the fundamental theorem of calculus, this integral is going to end up being the natural log of the absolute value of 2 minus the natural log of the absolute value of 1. And I could leave this answer like this, that this is perfectly mathematically correct. Your textbook will give you a different answer. The textbook will apply a property of logs, that the difference of 2 logs is going to be the log of that. So in this case, this is just the natural log of 2 minus the natural log of 1. So this is not calculus. This is a property of logs that if you wanted to go back and review some properties of logs, I have a video posted on that as well. And the natural log of 2 divided by 1 is just the natural log of 2. You can also see this by realizing graphically or putting into your calculator that the natural log of 1 is actually just 0. It's asking e to what power is going to give a value of 1, and e to the 0 is the value that gives, or is the power that gives the value of 1.